How's everyone? Life's good?
That's great.
Good. Your microphone is not the best. I don't know what's going on there. Okay. So the last time we started to talk about policy search, and then yeah, we jumped on policy gradients as well a little bit, I guess. And just as a reminder, we're looking into the case when we want to compress the policies. So we're hoping that if there is a way of compressing the policies, then with a compressed representation, we can be still computationally efficient in this simulation optimization context or planning context. And we saw that the first big blow on the plan is that, well, if you're demanding too much, you want to compete with the best policy within a class. That won't happen. So you can't compete with that. There is an MP hardness result. And so maybe the second best thing is to compete with or find stationary points, which may or may not give you the global optimal solution. And then the questions are, okay, can we get to this stationary points efficiently? Let's say with gradient descent. And what approximation guarantees can we get for these stationary points? So that is, if we are lucky enough to find a stationary point, we want somehow a guarantee that the value that we're going to get for the stationary point is high compared to optimal. And then the question is how high? I guess this should be actually a data here. Because usually like the suboptimality of the policy induced is denoted by data. And epsilon would be some inherent measure of like how good is the policy class in this case. And right, so we looked into a paper that is a recent paper. It just says that vanilla PG is not going to cut it at all, even though if you don't have any restrictions on the policy class. So you can represent all the policies, and then you use the vanilla representation, which means that you treat this stochastic policy as a big table. And there was really interesting research that showed that policy gradient can actually converge to the optimal policy. But then there is this sobering result that is very recent that we talked a little bit about the last time, that shows that this convergence is going to be slow in the sense that some constants are going to be just too high. So it takes way too many steps. It's like exponential in a bunch of quantities, even though there are other algorithms like policy iteration that are strongly polynomial for the same problem. So vanilla PG fails this test of whether on the simplest instance, like you want a universal algorithm, right? So that is not really sensitive to the choice of pi, but we see that like it can be pretty sensitive. If you choose pi very nicely, then basically the algorithm can just be very, very slow, even for cases where we know of algorithms which are really fast. And then I mentioned briefly at the end that maybe there is some hope, some variation, natural policy gradient, which we didn't much get into, but So maybe you can introduce some twist to the gradient descent so that the directions are improved, the search directions that gradient ascent makes steps into, and with that, there is the hope that this will converge faster. So today, we should continue this exploration of these policy gradient methods. And let's start with the simplest thing, the computation of the gradients. So can we even compute these gradients? So maybe eventually we will need to twist something or be clever about how we follow these gradients. But can we even get them? So to get this gradients, so this is gradient computation. So the first thing to look at is the policy gradient theorem. So PG theorem. Probably everyone heard about this theorem. I'm going to present a variant of it that is by, well, the proof is by boundary. And also in this recent paper, it's a very short proof. It's a very elegant result. But the policy gradient theorem has a long history. There is a deterministic variant of it, and that goes under David Siller and a bunch of other guys. And of course, Reach, setting there, pretty much Kakadi. Everyone did something with this, a lot of people. But the proof here is due to boundary and Rousseau. And the key idea is that we want to present, we want to have a single theorem that covers everything. And the proof should be easy. And for this, we're going to assume deterministic policies. And we're going to assume, so the policies are going to be, they're parameterized with some parameter. They're just mapping states to actions. And so the action space should be a subset of some vector space, I don't know, RP or something. And maybe they should have some connectivity properties or whatnot, so that these policies can be nicely differentiable. And you might be wondering about, okay, what happens to our nice case of finite action MDPs? So suddenly I'm saying that, oh, you should have a continuous action space, what's going on? So if you had a finite action MDP, then you could choose A to be all the probability distributions over A. So this is, these vectors in 0, 1 to the power of A, such that they sum to 1. All right, so you redefine the action space. So there was this original action space, and then there is this new action space. And if you had a stochastic policy over this discrete action space, then obviously, so if you had some policy that was mapping S to M1A, then by definition, this is a policy that's mapping S to A tilde. So you have your continuous section space. Well, we also have to do something about the transition probabilities and everything, because now we have this continuous section space, which is the simplex. So if you had your original MDP and it was like P and R, these are the transition dynamics and the rewards, then we're going to define this new P tilde, right? Which is going to take actions from A tilde. So here, P is the structure of all these distributions where A goes over all possible A's. And now P tilde is going to be this other structure where A tilde is an element, little a tilde is an element of big A tilde. And so P tilde, A tilde. So what is it going to do? So the transition, the probability of going from S to S prime, unsurprisingly, so A tilde is a probability distribution now. So I can, this is going to look funny. So A tilde has all these components, so I can index it. It's a vector. And we had all these transitions for all the base actions, all the actions I. The actions are called I now. And you can just like sum up all these probability kernels, weighted with the probability of choosing each of the kernels, right? And you can also introduce R tilde, which is going to be this structure that you have this R of A tilde, or all little A tilde, and R of A tilde at S is going to be very similarly just the expected reward undertaking this stochastic action A tilde, right? So this way I created from an MDP. So you start with an MDP SPR, sorry, SAPR, and then you end up with an MDP M tilde with the same state space, A tilde action set, P tilde stochastic kernel, R tilde immediate reward function, in such a way that if you had a stochastic memoryless policy of M that's trivially mapped to a deterministic memoryless policy of M tilde, right? So this is just this identification. So remember that if P is this stochastic policy, then well, we can define P tilde of S as P of S. it's the identity, right? Like that, they're the same. And so the property of this is that, well, you can do this translation for any of the policies, not only the memoryless policies, of course. And this translation has the property that the value functions, and it's not hard to see, are going to be translated. So if V tilde of pi tilde, or pi, is the value function of a policy pi in this MDP M tilde, then it holds that if you start with a policy in the original MDP, you take its value function, or you take its value function when it's viewed as a policy in M tilde, you get the same values. That's pretty trivial because of the definitions of the stochastic kernels and the immediate rewards, right? And so it follows that, you know, the optimal value functions are the same. Similarly, q of pi is equal to q of tilde of pi, and so on and so forth. So if you're interested in computing an optimal policy in M, long story short, you can go and compute optimal policies in M tilde, focusing only on deterministic policies. You don't need to consider anything beyond that. Okay. So deterministic policies of M tilde suffice for M. So because of this, it's fine to consider just deterministic policies and the case when you have this continuous section set. All right. Differentiability properties also are inherited. So if you had a differentiable policy with respect to some parameterization for the original MDP, you end up with a differentiable policy with the new one. That also goes. So for the purpose of this theorem, we're going to assume that A is a subset of R of P, and there is a policy parameterization that's given to us that gives us a deterministic policy. And right. And then the theorem goes like this. We're going to assume two things. Or one thing. So we're going to assume that the map that takes, okay, so theta here is an element of RD. Okay. So X is also going to be just stand for a d-dimensional vector. So it's like a potential parameter vector. So you take the map that takes a parameter vector and maps it to this value. So it's m of pi of x applied to q of pi. So recall that m of pi applied to q function, that is just, you know, like at a state s. That's just the abbreviation that we're plugging in pi of s into the action component of the action value function evaluated at s. So it's a plug-in operation. There's just an abbreviation for that. And so this creates a value function over the states. And we had, okay, like the notation that I was using before is that you have the future discounted state occupancy measure under the initial distribution mu under some policy pi. So that gives you a state distribution over the states. And all those distributions are seen as row vectors. So you can just like multiply. This is kind of like a column vector. And this is a row vector. You can just multiply them and get this number. All what this means is that this is the inner product of these two guys. It's just like the average of the q values when in the q function of pi, you're plugging in this policy pi of x. And you were taking the average q values or action values under this plugin with respect to the state occupancy measure. Okay, so that's one of the maps. So let's call it F. There is this other map which simulate takes an X, and now it just takes the same discounted occupancy measure, but under policy pi of X. And it applies to the action value function, sorry, the value function of policy pi. And so, okay, fine, we have these maps, and this is indexed by pi. This is also indexed by pi. And let's fix some theta in RD. Let's call it theta naught in RD. And the objective function that we want to maximize as a function of theta is just this. Sorry, that's not that. Jumping ahead. It was just you take this initial state distribution mu and you're integrating the values of policy pi of theta with respect to this distribution. And the theorem says that assuming f pi theta naught g pi theta naught is C1 continuously differentiable in a vicinity of theta naught, then the gradient of J at theta naught is going to be equal to something really simple. It's the, oops. Is the gradient of nu theta mu pi theta naught m of pi x and q of pi theta naught. Right? So if I want to write this out, so you might think that I'm crazy that I don't like to write these sums, but I really don't like to write them. So writing these sums is just like way too much work. But sometimes it's easier to see what's going on. So this is what's going on here. Oh, and then x equals theta naught here. So this last expression is really the derivative of this big sum, big weighted sum, but then you plug in x equals theta naught. Right? So it's basically, it's better be the case that, well, if we think that this should be differentiable, that somehow q should be differentiable with respect to the action argument, and maybe pi should be differentiable with respect to x. So I mean, like that's a sufficient condition so that this expression is differentiable. And then you imagine that you just use a chain rule to get everything going. All right. Do you have any questions for this?
Yeah, Shaba, I have a question about, like, in the first expression, Why aren't like the pi theta naught that's appearing in the new hat in the Q? Why is that also not pi x?
Oh, because you're only differentiating with respect to this, right?
Yeah, but why is
So,
that correct? Like, why is it correct to not differentiate with respect to the other things?
oh, like that's the theorem, right?
Oh, okay. So this is what we want to prove, right? This is not like a
Yeah,
statement of.
like this
Okay,
is the theorem statement
right, right.
that
Okay.
from that f and g are differentiable
Mm.
at pi theta naught. I guess that's where you should have it. From this, it follows that the j is differentiable and the derivative follows this simple expression.
Yeah. Okay.
So this gives us a vehicle to approximately calculate derivatives then, right?
Right. Okay.
Right? When one thinks about this question, what might be surprising is that you start with this expression, the theta only appears there. But somehow the mu, yeah, we know that in here, there is this discounted occupancy measure hidden, and then there is the reward hidden as well. So it's like this is the inner product of the discounted occupancy measure and the reward, right? But somehow, like, we're not talking about the reward differentiability or the differentiability of, I mean, in a way, we're talking about the, oops, oh my God, the differentiability of the occupancy measure, right? So G really is about the differentiability of the occupancy measure. F is really the differentiability about this composite function here. And from this two differentiability properties, we want to claim that the derivative of this objective, which is just this integrated value, takes this simple form. Make sense?
Yeah. Yeah.
Right. So for the proof, we only need to remember one thing about calculus, which is that if you have a function of two variables, u and v, and you want to calculate the total derivative of this function at xx, and it's a sufficiently nice function. So this is where this continuous differentiability comes in. Then you can do that by taking the partial derivative of f with respect to the first variable u, plug in x and x, and sum this up is taking the partial derivative of f with respect to the second variable and plugging in x and x. And yeah, so this is like, calculus 101. This is where we are using that f is continuously differentiable in either u or v. It's actually enough if it's continuously differentiable in either one of them. If it's continuously differentiable in both of them, that's great. But you can still get away if it's only continuously differentiable with respect to one.
Wait, shouldn't there be a u and a v on the right hand side in the expression? In the expression on the right hand side, shouldn't it be fux plus ddv of fxv?
Yeah, this is where we are getting into these nasty issues about how do you use notation in this in these cases where you need to designate partial derivatives. So here I'm using the convention that I'm naming some variables of the function u and v, and then I can just designate partial derivatives based on this naming convention. So this, by definition, means taking the derivative with respect to the first variable, and then I can plug in whatever. And then this, by definition, means taking the derivative with respect to the second variable. And then you can plug in whatever. And I happen to plug in x and x. So for both u and v. There are all these crazy different notations, and like, I don't know, like I don't like any of them. Maybe one better notation is delta 1 or something like that, or f prime 1 or like whatever. It doesn't matter. You understand what I mean.
Yeah.
All right. So, okay, proof. Almost every proof has to use the value difference identity. So that's what we do. So recall that the value difference identity, I don't know, of this two policies. It was like, okay, what's the value function of the first policy? Well, it's this inverse thing applied to the reward of this thing minus the value function of the second thing. And I can plug this out or pull this out. There's no plugging out, there's pulling out. And from this, you see that this is the same thing as T of pi prime applied to V prime. That is negative and negative, so that's a plus for V prime. And minus V pi. So that's the value difference identity. Okay. And we're going to apply it to when this pi prime is, okay, this is a bit crazy. I don't do this. I want it to just like, okay, so we want to apply it when pi prime is, I don't know, pi of x. And pi is just pi of theta with some theta. And multiply the whole thing from the left by mu. So we get mu v pi of x minus v pi of theta is equal to, if I multiply this by mu from the left, I get the discounted occupation measure of pi of x, because pi prime is pi of x. And I just write the rest. Oh, and this t of pi prime, v of pi, it can also be written as m of pi prime, q of pi, right? Because you can expand this t operator into two. So t of pi is equal to, or t of pi prime, if you wish, is equal to, applied to some v, is equal to m pi prime r plus gamma p of v. And if this v was some v of pi, then this is what we call q of pi. So it's like this crazy jungle of notation that we use in reinforcement learning. Okay, so they're just like identities. Nothing really happened there. And now we have m of pi of x and q of pi of theta minus v of pi of theta. And now take the derivative of both sides with respect to x. And recall that this is a function where x appears twice. So I'm going to just make this two axes separate. So create this function f, u, and v. So one of the arguments is this u here, and the other is this v here. Okay. So that's my f function. And I need to take the derivative of f with respect to x when u and v are the same. They're x. So that's gonna be the derivative of f with respect to u. And then plug in x, and then the derivative of f with respect to v, plug in x. So all right, so just have to record everything. Oh, if I take the derivative of the left-hand side, the second guy, v of pi theta, that's a constant. Doesn't depend on x, so the derivative of it goes away. And I get the derivative of j at x. And then on the right-hand side, I just need to copy. And I have to subtract the derivative of nu tilde u pi of x v pi theta. All right. So now just make everything equal. So choose x equals theta naught. So now, all right, we have this notation for the gradient theta naught. And so what happens is that that is, if I choose x equals theta, then here, if I choose x equals theta, then what appears here is v of pi theta, right? So when x is equal to theta, then you're just plugging in the same policy into the action value function, you get the value function. And then you can see that that's the same term as here. So the first and the last term cancel under this assignment. And what remains is the term in the middle and nothing else. So let me just write that. And that's indeed the expression that we said we're going to prove. So value difference identity does the trick always. There were some half-full cancellations. And other than that, it's just like rules of differentiation. The magic is the value difference identity, really. And that's where the useful things are happening that allow the cancellations. All right. Good. Any questions?
Okay. Why did we need the policy to be deterministic?
Why did we use that the policy was deterministic? Well, it's a good question. I guess the way I'm writing things, you don't need it. Because this M operator is defined no matter what. And I guess it's... I guess if you don't want to write the theorem in this form that is shown here, then you don't need to do this. Good point. I guess maybe what comes next, that it's useful. What I was doing before, that basically showing that deterministic policies suffice, because then if you have this formula and you think about the stochastic policies as maps from states to this continuous action space, then you get the other policy gradient theorem that more people will know about, right? So there is this other form of policy gradient theorem which says that, oh, if you have a stochastic policy over a finite action space, then the derivative of this policy takes a certain form. Well, that's the same as this, clearly, right? So you don't need it, right? So if I have Yeah, I don't know. It appears to me that we never used anything about like, we just said that these maps should be differentiable. These maps are well defined. And then just use either identities that hold no matter what, or use just this partial derivative rule, and then there is nothing else. All right, good point. So the classic policy gradient theorem looks at this expression, and it just expands on it, right? So if I have a stochastic policy, P theta, so it maps S to M1A, then we usually write this as, you know, like you have probabilities assigned to each of the actions that sum to 1 for each of the actions. And then this expression, nu tilde mu of pi theta and pi of, I don't know, v, q of pi theta can be written as this double sum over the actions, and then take the discounted probability measure. And then there is the sum over the actions. And then there is this probability assigned to A, and Q of pi t as A. And what the policy gradient theorem tells us is that the gradient of J with respect to theta is equal to the derivative of this, which V equals theta, and basically you can move in the derivative here. So this is equal to, for the stochastic policies case, this expression that people might have seen, right? So there is this form where you just take the derivative of, oops, sorry, of the policy, and then you plug in theta there, and then qp theta as A. And oftentimes people also add the twist, noting that if you take the log of pi v as and the derivative of that, the derivative of the log is 1 over, so this is pi v as, and then the numerator is going to have the derivative of the probabilities. And so with this identity, we can write that the derivative is further equal to sum of s nu tilde mu pi t theta s sum over actions, and then pi VAS. So I multiply, then I need to divide. So if I divide here, I multiply back. So now this is going to assume that these probabilities are positive. It shouldn't be 0, because otherwise, how do I divide with them? And then just write the derivative. Okay, so then you take a q of pi tilde as A, and then correlate it with the derivative where v is going to be equal to theta. So since that doesn't appear there, I can put a theta there. Okay, so this is the form that most commonly cited, I guess. But all of these forms are pretty useful. Oh, I guess maybe the point of the deterministic thing is that also applies when things are deterministic and you have a continuous action space. So it's like that form is not sensitive to whether you are in a deterministic case or not. It doesn't matter. That's just a general form. Okay. All right. So from this form, we also see how we can use simulation to get gradient estimates. Some estimate of the gradient with bounded noise. How to do that? You have a simulator. Can someone tell me how they would do that? Based on, let's say you have stochastic polysystem and you want to use this expression. That's the hint. So you want to avoid these big sums over the first big sum is over all the states. The second is like, maybe you don't care about that. The sum over the actions, like who cares? Like if the action space is small, then you don't care about that. If the action space is big, then you could say that, oh yeah, like let's also sample there. So how do we do this? Like we should use sampling, right? Come on. So how would you use the simulator? It's probably too much to type, so if you have a mic, you can just speak. I'm looking for simple things.
Sample SNA from the policy, then do rollouts to estimate the Q pi.
Right. So we need to produce a sample from SNA. But we have this new tilde. So new tilde is like this discounted occupancy measures. It's not really a probability measure. To make it a probability measure, we have to normalize it, right? So this thing sums to 1 over 1 minus gamma. So we need to multiply it with 1 minus gamma, right? Then 1 minus gamma mu tilde mu pi t theta SA. But if you multiply it with pi SA, then you get this. Discounted probability measure normalized now over the state action pairs. And then if you sum up this over SA, then you get a 1. So this is a bona fide probability measure. So we can sample from this probability measure. So let's say you sample SIAI from 1 minus gamma times this thing. Where I goes from 1 to n. So that's step number 1. And step number 2, as Wesley said, roll out from SI-AI with pi theta. Maybe for how many steps? Many. Something like this many steps for epsilon error. So this is going to be a bit biased. Fine. Very small bias. We're going to set the bias very small. Hopefully that doesn't bother us. We would need to worry about, if you want to prove anything about this procedure, how to control the bias and how big that should be. But for now, let's just say, okay, we can do this. Bias is going to be small. And to get the return, so then you get this Q hat values, which are just for each of this index I, you get these values, and maybe you do this I don't know, J times, M times. So all of these are independent. So independent rollouts. And then you might wonder about, okay, should I do one rollout or multiple rollouts? What do you think?
Actually, before that, so for the number of steps, can't you just use a geometric random variable with the parameter of gamma? Like, so choose the rollout length and then run it forward for that many steps.
Oh, that's a good point. Yeah. So if you don't want bias, yeah. So then just roll out for n steps. Yeah. And that's the same idea as, like, we didn't talk about how to simulate SI-AI. The other question is how to simulate SI from this discounted state occupancy measure. So there the idea would be to start running the policy, and in each time step, before you choose the action, you flip a coin with a bias of gamma. And if the coin flip is 1, so the probability of 1 is gamma, then you continue the process, otherwise you stop. And you declare that, wow, this is the state that I had. So that's the same geometric sampling as Roshan mentioned. So that's how you do it, and then you can do this rollout. Yeah, so the next question is, should we sample, like, should we have multiple rollouts to estimate the Q pi and then maybe refine it, or like just have one? What's your gut feeling? Just quick. Yeah, you can type multiple or not. Just one. Okay, Roshan started with 1. Is it, Roshan, because you are so lazy that you don't want to do more work?
It's because you have to pick a constant, and 1 is the best constant.
Yeah, it's like, it's really hard to pick anything else. Yeah, Wesley say SGD style. Yeah, it's one rollout. I think I would bet on one rollout. If you want to minimize the variance with the minimum amount of work, I would bet on one rollout will do it. Without, like, with this vanilla sampling, like, if you're not trying to be more clever. Okay. And are we going to be able to control the variance of this estimate? Okay, so what's the estimate at the end, right? So we didn't say what the estimate was, but the estimate is going to be I don't know why I denoted by that. Oh, I have to pre-multiply with 1 over 1 minus gamma. That's a bummer, but I have to do that. And then I accounted for this guy, this guy. This is going to be Q hat, and then have to also add that. All right. And if you think about it a little bit, yes, you can control the variance. The not so nice thing is this 1 over 1 minus gamma, but what can you do? And also the scale of this is in general going to be 1 over 1 minus gamma. So the scale of the whole thing is pretty large. So one more little thing. It's not hard to see from this variation of the policy gradient theorem that if instead of this Q, you have Q minus any function of the states, then that's also a correct expression. And the reason for that is simply because the sum of these probabilities under a policy, they are 1. So if you take the derivative of both sides, the derivative is 0. And here, B doesn't depend on A. So that can go in front of the sum. And you're left with the sum of the derivatives. So that's the term that comes from B. So B of S is going to multiply the sum of the derivatives of the policy. And that's just 0. So you can play around by, this is called baselines, and then people spend a lot of time of wondering about what's the best baseline to reuse the variance. And that's, yeah, I mean, the variance on its own is, okay, maybe just a big number, but it's finite. So, and it's proportional to the effective horizon. So in terms of, like in simulation optimization, can we do this in polytime? It doesn't really matter whether you reduce this variance or not. You can reduce it by something, but it's not going to do magic. Maybe the horizon dependence would be improved. So that's what you can achieve with it. Nothing much beyond that. And there we have already seen that if we run vanilla PG, then we would be in trouble, so we can't do that. So what to run? So vanilla PG, vanilla policy gradient was too bad. So then there is this other idea of running what's called natural policy gradient. So let's talk about this a little bit. So there are other ideas. So maybe vanilla PG is not good, but maybe you could have something like a Frank-Wolf type algorithm. Bandari and Russo are talking a little bit about that. I don't know of any results for these that would work with function approximation. So maybe there are some other variations that are hopeful. The only result for which I know results when you have real compression going on is some version of natural policy gradient. We'll see how that goes. So natural policy gradient is is the following algorithm. So you have this policy parametrization with pi theta, and you define this matrix. This is called sometimes the Fisher information matrix. So you take the discounted state action occupancy measure, and then you take the gradient of the score function of the policy, that's the log probability derivative. So that's the score function itself. And then this gives you a vector. And right. And you do this twice. So you get an outer product. So you get a matrix. And this matrix gives you, like this is a matrix for any state action pair. And you integrate it out with respect to the discounted state occupancy measure. All right? So that gives you a D by D matrix. And it's positive semi-definite for sure, because all these rank 1 outer products are positive semi-definite, and the sum of those is still positive semi-definite. And natural policy gradient says that, well, don't follow the gradient, but rather the update should be of the form that you take the pseudo-inverse of this matrix and you use that to rotate the gradient of J of theta. Right, so that's the definition of natural policy gradient. Some people like to draw connections to information theory at this stage. I kind of like try to trace back whether there are any rigorous claims that you could make concerning these claims that so somehow natural policy gradient in exponential families is kind of corresponds to like following the gradients on the probability manifold defined by the curvature of the space, the local curvature of the space. So you have this, like in general, you're in a probability simplex, it's this body, but your parametrization chooses some thin shell on it, and then you can travel on this, and then there is some curvature, and you can define distances on this surface, and you want to take into account this inherent metrics of these distances. And for this, you need this probability measures. You want to be on some simplex or generalization of a simplex. And their natural policy gradient does have some asymptotic theory that says that asymptotically it's Fisher efficient, so on and so forth. But when I try to apply these ideas in this setting, I don't know, I can't complete them completely. So I can't name the probability space where I would have this curvature and whatnot. But intuitively, this feels like the right thing to do, the thing to do if you have these policies. You might question why this weighting, why not some other weighting? Well, for one thing, this weighting seems to have some nice properties. Okay, so maybe we don't have like a fully rigorous justification of why to choose this particular metric. At least I don't know of one. But this has some pleasant properties. So the pleasant property that I'm talking about is this. So the theorem says that, okay, let's normalize this, this direction that we should be following. Oh, this plus sign is the pseudo-inverse. So if in case you have a matrix which is singular, so it's just positive, semi-definite, not positive, definite, you can't invert it, then you just solve the least squares problem to get the minimum norm solution. So that's the pseudo-inverse. And so this just says, well, I don't need this theta there, t there, that this is equal to, I'm going to be a little bit sloppy. So this is the minimum norm solution if there are multiple solutions of a least squares problem. And in the least squares problem, you get the same weighting as what we had before. Okay, you know what? I don't have enough space here. That is 2 norm. No. And we're gonna fit, so this W is in RD, the same as theta. And we take, oops, sorry, we take the score function as features. Right? So this is a d-dimensional vector. Think about this as features induced by the policy parametrization, and fit to this the action value function of the policy. So the action, sorry, not action value function, the advantage function. The advantage function is just the action value function minus the value function. So if you have a suboptimal policy, then for some actions, you get a bigger value than the value, and this is positive. If you are at the optimal policy, then you get a 0 for the optimal action, and for all the other actions, you get something worse. So that's the theorem. So why does this work? Well, it's just a computation. So if you compute what the solution of the least squares problem is, well, think about it, right? So there is the feature matrix, the features that you're fitting, and you're fitting to this thing, and okay, the moment matrix induced by the features appears. So what is that moment matrix? So moment matrix is the outer product of the features integrated over the measure. Okay, so that's the moment matrix f theta. So that's, and then the pseudo inverse in least squares solution, the pseudo inverse of that is multiplying the features correlated with the target. So what are the features? These are the features. This is the target. And okay, the policy gradient theorem, this one here said that, yeah, like we have the features. Okay, this is the advantage function, but whether it's the advantage function or the action value function doesn't matter, because we said that we can always subtract the baseline, right? right? So that finishes the proof. Just least squares. Just looking at identity. Now, if you start at the right-hand side, does the right-hand side depend on? Yeah, it does, right? So from this, it doesn't immediately follow that this would be independent of the parametrization, but at least this choice has the property that if you reparameterize the policies in a smooth fashion, then this expression is going to be invariant to the reparameterization. So if you map back to, like you have a new parametrization, like a theta prime or like a, I don't know, kappa parametrization, and you map back what gradients you would be getting there, then you follow the same directions. So with the infinitesimal steps, the gradient flow would be invariant to reparametrization. So that's one pleasing property, which, by the way, you can have that pleasing property for many different expressions. So if I take this expression and I multiply it with some other matrix, that only depends on the policy and not on the parametrization of the policy, then that expression will also have this property, right? So it's not unique in this sense, but at least this has that property. All right, so how does this work actually? So one simple case is the case of Boltzmann policies. With linear parametrization. So that's a case that we like. Okay, this should be just proportional, right? So in this case, if you calculate the derivative of the log of these probabilities, they become the features and centered. So it's going to be prime, and you're just centering the features. And so in this case, NPG is going to take this form of the update is eta times WT, where WT. So let's call this this guy here. Let's call it psi theta SA. So it's almost like the features, but they're centered, and the centering depends on the parameter that you are at. And so you can take this squared error and then take these features and fit the action value function. And so that's NPG. In the case of tabular, okay, so that in the tabular case, where the phi's are, like the tabular features, so you can represent all the policies, then this algorithm has known good properties. It converges. in time that's polynomial, so you can run it and so on and so forth. For the case when you have these features, so not tabular, we don't know much about it. What we have some results about is this Q and PG algorithm, which is a variation. It's going to be the last thing, don't worry. And so here you get the same thing, W integral, but you say, the centering, yeah, I don't know. Maybe let's just use the features. Oh, this action wave function, since we are not centering, maybe, sorry, since we are not centering, maybe don't use the advantages, use the Q function, the action value function itself. And so this is called Q and PG. And now remember what Polytech was. So Polytech was basically the same as here, except that you have an optimal design. So you replace this nu with nu hat, which is based on G-optimal design to control the extrapolation errors. And Polytech is basically almost the same as Q and PG. I don't know whether we should make distinctions of this level of granularity. So these algorithms to me are basically the same. I don't think that we should be really too picky about these names, so to say, but it's worthwhile to talk about what impact does this choice have. So in planning, maybe you have the option to calculate the optimal design, and if you do, then for Polytech, we already have seen pretty strong guarantees. So maybe it shouldn't be surprising that for Q and PG, we also can get some guarantees. And indeed, you can get some guarantees, but I'm not going to go into the details too much of that. But these guarantees tend to suffer some extra cost. So in Polytech, there is this blow up of the approximation error by a factor of square root of d that comes from this optimal design. And in the analysis of Q and PG, there is some other blow up factor, which is related to the deviation of where the optimal policy wants to go versus where the initial distribution wants to go. So this blow-up factor is made dependent on the MDP's properties. So this C epsilon appears in a bound. And also the bound, I think it's like the approximation error dependence is a little bit weird. It's like 1.5 gamma to the 1 minus gamma to the 1.5. In Polytech, we had 1 over 1 minus gamma. The other terms are very similar. And the analysis of Q and PG is really based on the mirror descent analysis that I was also talking about. So in terms of the analysis, where we have some result for policy gradient, is where it becomes basically mirror descent, or some variation of mirror descent. Then we can use the mirror descent analysis and we can get some results. Having said this, I think that there is some merit of going away from the optimal design. Definitely, we want to see whether you can get this nice result. So that's a nice open question. Whether we can get this very nice result without demanding that design points of an optimal design are handed over to the planner. Right. So that's how much I have for today. There is one more part, which is like how good are the stationary points in policy gradient. But I'm not sure whether it's worth to spend too much time on it, because we don't really have algorithms that would reach those stationary points. So yeah, we can ponder about how good they are, but the only algorithm for which we do have for functional approximation have a guarantee is the skew NPG algorithm, for which we kind of already know what's going on. All right. Are there any questions?
I have a question about the last thing you said. Why, like, what stops gradient descent from reaching a stationary point?
What drops? What?
Like you said that we don't have algorithms that reach those stationary points. So why doesn't gradient descent reach a stationary point?
Oh, like polytime and whatnot, right?
But even then, if you're just looking for a stationary point, or I guess it would it would be not quite a stationary point. It would be like an epsilon close to
No,
being
even epsilon stationary points you wouldn't reach. So the result, I don't know whether my browser is still open there, but the last time you remember, we were talking about that already in a tabular case. If you take the vanilla parametrization and you run policy gradient, then it takes this horrendous amount of time to reach an epsilon stationary point. It was 1 over epsilon squared, that's fine. But then there was the size of the state space raised to the, I don't know, maybe the effective horizon or something like that.
Okay.
Remember that?
Yeah, I thought that was like the lower bound was for like, was that the one based on the independent set construction?
No, that's a different thing. So that's not for stationary points. That's for policy search. So that kind of kills policy search, or hopes that for policy search we will have efficient algorithms in general. So you might still have some special cases, efficient algorithms. But for policy gradient, okay, so this is not for the, sorry, I misspoke. It was for the softmax parametrization, but for the tabular case. And this is a lower bound on how many iterations you're going to need to get to a constant accuracy. And that's like, okay, like you don't want to run this algorithm. So for NPG, on the other hand, for the same case, for the NPG, for the same case, maybe we have a uniform upper bound. So you can't really rule out that there is some algorithm that reaches the stationary points in reasonable time.
Yeah, I was thinking that, yeah, I remember this lower bound, but I was thinking that this was basically because of softmax that the difficulty was coming in.
It's softmax and yeah. But okay, so you want an algorithm which it works regardless of the parametrization chosen. I mean, like you need to choose the game, right? Or is it going to be specific to some parametrization, or we want to use something like NPG, which is somewhat parametrization independent?
Yeah, I was thinking just the algorithm specifies some metric on the space of policies, and then it takes gradients with respect to that metric. So it may be more general than NPG because the algorithm can pick a different metric than the Fisher distribution.
Yeah, right. Yeah, so we don't, but I'm just saying that we don't have a positive result for the case when some real compression would happen to the policy space, apart from the result that is for basically mirror descent. And there, it's like, if you look at this, so you start and you say, okay, let's run NPG, but then we change it. It's not NPG anymore. And I suspect that to really get it off the ground, either you, like if you have an optimal design, then you can switch to this other metric, this mu hat distribution, and you will really get a nice uniform bound. So we are kind of drifting away from policy gradient. And then there's a question of like, what is the boundary of like, when are you going to stop saying that this is still policy gradient? Yes, all of these algorithms are related to each other. All this is just policy iteration, if you wish. And I don't think that there is much value in trying to create boxes and then put all these algorithms into these joint boxes and like discuss where is the boundary of the box and like my algorithm belongs to this box, your algorithm belongs to that box. No, that's like we should solve the problems. And as far as, okay, so for me, the policy gradient idea, okay, I didn't talk about that part, but it's like gradient ascent. Like, how do we prove that gradient ascent works? Well, it's not like the mirror descent proof usually. It's like you assume gradient dominance, you assume smoothness, you prove this, and then from that, you get some convergence rate. Mirror descent proof is a slightly different animal. Yeah, so let me put it this way. The techniques that come with gradient methods didn't prove yet to be too useful to get strong results in reinforcement learning besides the tabular case. Okay, I have to modify that too because there's the LQR case and like there are some other corner cases, but like for this featureized case, which like this compressed case that I like to think about, I don't rule it out that one day we couldn't do it. Maybe it is possible to do it. Maybe you twist the gradient in nice ways and then nice properties are gonna show up. I'm saying that, yeah, as of the moment, there are no such results.
Yeah, and I was thinking that the softmax is especially a bad fit for any sort of gradient method, just because the optimum lies off at infinity somewhere. So it just seems weird to use a gradient method to try to get to infinity.
Yeah, exactly. Without step-side adaptation is especially problematic, right? Because you have like this really high curvature, like you get into this flat region and you're supposed to travel a lot there. Like, I don't know, it feels, yeah, quite bad as a choice. Yeah, we should mention Qincheng's work, right? So in one of the previous papers, we were trying to replace the softmax transform with some other transforms which might have better properties, and then lo and behold, there are much better choices than the softmax transform. But somehow people are hung up on this. I don't know. And there is also this nice coincidence with mirror descent. It's almost mirror descent, right? Like what you get. And for mirror descent, we also know that even for mirror descent, this is maybe not the best. So, but yeah, it's tolerable. Like for mirror descent, this is a tolerable choice. Yeah, it's like in this area, there are very many more open questions than questions that have been positively resolved, even though during the last year or so, there's been so many results, maybe last 2-3 years actually. So many results. many interesting results as well. Still kind of like they don't bite for me, but don't give up.
So what should we use instead of softmax? You said
so you can what?
Oh, you just said that you guys had some different forms that seemed to be a better choice.
Yeah, so you could take the absolute value and the square root and normalize.
Okay.
I forgot the name of it. Like Jincheng, how did you call it? It's like the physics name.
It's gravitational
escort map. Yes, the escort map. Yeah, use the escort map. Actually, it's maybe not a bad choice. So, okay, questions. So what parametrization? Maybe the escort map does it all.
Is the escort map X over 2 norm of X?
It's like if you have this scores, so you have a score vector, which I don't know, a-dimensional, then you take square root of SI and then some of this. Is it right, Jincheng? Okay.
And is this better because it doesn't have as many flat regions?
It's better because its curvature is more friendly to the gradient.
And it's not differentiable at 0, right? Or is it?
Is this you want to stay away from 0.
Right. Okay. And is it possible, like, so one way of thinking about this is which parameterization to use. The other way of thinking about it is what is the induced metric on the space of policies that is equivalent to this parameterization?
Yeah, I don't know, man, this metric business, I have not seen a I mean, like, Amari is really crazy about this natural gradient stuff. And maybe this exponential family, it's a good thing, but beyond the exponential family, it's really hard to see in what way does it have beyond some asymptotic results that people have proved. So it's like local directions chosen somewhat better, but like it's not obvious to me like in what way it's guaranteed to be a universally better way of going about things. So the only positive result that I know of is that asymptotically this minimizes variance for the usual, I don't know, standard problems with log loss and whatnot. And you can achieve the same with constant step size and averaging in a bunch of cases. So there are some alternatives of it which are maybe even simpler. So it's not obvious to me that you need to think about this. I mean, it's an interesting space. It's interesting to think about it. Sometimes it creates very interesting. I think that for ICA, independent component analysis, it creates some really interesting algorithms which have some good properties, maybe not provably good properties, but it seems to, or maybe just people so far didn't pick it up, but empirically it seems to give something interesting there. But is it going to be, like the tool to use in reinforcement learning? It's a little bit unclear. It's definitely something to play with, but I like to be a little bit more generalist. I like choose the metric in whatever way, and like that's just like designing an optimization algorithm, right? And then you were just saying that design a second order optimization algorithm in the best possible way. that's more general than saying that follow natural gradients.
Yeah, I guess it's just for geometric intuition, right? Like if you're looking at it in a differential geometry point of view, then for every gradient you ask yourself what is the metric that this gradient is following, and if it's not following any metric, then it's not a gradient, right? So.
Even that is not true, right? I mean, maybe it's locally not steepest descent, but that doesn't make it a bad direction globally.
Yeah, right. Yeah, but then I wouldn't call it a gradient algorithm.
Yeah, but who cares? Yeah, okay. So maybe we are saying that, okay, if you want to stick to a gradient algorithm, then it has to have a gradient interpretation. I don't know. It feels a bit narrow to me. Maybe to me the gradient idea is to, okay, you want to somehow calculate these gradients, approximate the gradients, and then make steps with them, like in the parameter space, but there you should allow yourself to, like introduce some transformations of it. Of course, computational cost is all that matters. So if you introduce matrices, I think that's still fine, because we would be very happy to be poly time and like a d squared here and there. At this stage, since we don't have any results, it doesn't matter at all. Or dq or whatever it is. Yeah. So, okay, yeah, like I just wanted to finish. The other is like, I don't know, adaptive directions or step sizes. Right, so the directions is a little bit more general than the step size, which is just like, how long do I go along this direction? But already, so now I'm going to advertise a little bit of Yingcheng's even newer work. Already there, we know that there is a lot to be gained, especially for parametrizations like softmax, maybe that you want to discard. But you can kind of undo the bad things that a parametrization is doing by being more clever about step sizes or directions.
How do you guys adapt to the step size? Some like tractable line search?
No. It's somehow simpler than that. So the step size, the advice is to take the step size based on the smoothness of the objective function of where you are. And so if you have some guess, and based on the structure of the reinforcement learning problem, you can have a guess of like how this changes based on location, and you can make the step size to change with the local smoothness. So these objective functions are not globally smooth. Often they are just locally smooth. So the smoothness constants vary in a great deal. And so you make the step size dependent on the smoothness at the location where you are.
And so how do you compute that?
You just compute an upper bound on the smoothness.
Oh, okay. So is it the local?
It's local. Yeah.
Okay.
Yeah. It's like you look at the analytic expression of like how does the smoothness upper bound looks like, and then you say, okay, let's plug this in. That's how it depends on my maps and whatnot, the known quantities. You can plug it in, and it works way better.
So I guess the quantities you look at are just, I guess, like the Q function. So I'm just trying to like think, like, what local information does it use?
That's like how the policy looks like and how the Q function looks like. Yeah.
Okay.
I guess maybe the Q function doesn't even matter.
Okay, I wanted to ask another question that maybe this is unrelated. Somebody else seems to have a question. So this is so in the policy gradient theorem, like it looks like one of the conclusions from this proof is that it's only like only first order quantities show up, right? So basically, you don't care about how the change in the policy is changing the occupancy distribution. You just care about how it is changing the one-step reward of the Q function, right?
Yeah. It's like a switches the like crazy. Let's think about all the future consequences of the change. Like that's the derivative with respect to the occupancy measure, to just like a local consequence, which is like, okay, locally how I, through the Q function, through the action values, like how sensitive I should be to changes to parameters.
And even the change in the Q function, it's almost like you don't care about the continuation part of the Q function. You only care about like the one-step reward part, right? Because you're assuming that the Q function has remained the same, but you're calculating sort of the change is coming from M pi, right? Like the.
Okay. Yeah, so you're not taking the derivative of the Q function parameter itself. That's what you mean, sure.
Yeah.
Yes.
Yeah.
Yes, like.
Yeah. Right. So
but the expression is unwidely, right? Like it's very different than what we started with, which was occupancy measure times reward. So and here it's like suddenly we don't have reward. Like we summarize the futures through that, and okay, the occupancy measure is there. So if you wish, like we swap the reward with this derivative expression. That's what's happening.
Yeah, so I guess what I was trying to say is that somehow when you're doing some sort of value iteration, you kind of have this very strong one-step flavor to it, that you just, every time you do value iteration, you're kind of updating things in a one-step manner. And with policy gradient, that is obscured because you're somehow taking this expectation with respect to the occupancy measure. But I guess the point is...
Yeah. Okay, so
so my point just to finish was that, so maybe all of that extra information would be hiding in the higher derivatives, right? But when you take the first derivative, then somehow it has this one-step update kind of thing, right? This immediate consequences. And so I'm just like, this is just an intuitive thing that maybe like if you take higher and higher derivatives, then you should recover sort of the longer term consequences. But maybe
I'm a little bit surprised that you mentioned value iteration. Maybe you wanted to mention policy iteration, right? We're trying to improve a policy here. And if you look at this expression,
yeah, I guess both of those have that one-step flavor to them, right?
Both of?
Both value and policy iteration have this sort of one-step flavor to them, right?
Right, but okay, so policy gradient is really like a smoothened version of policy iteration. If you started this expression, it's clear, right? Because in policy iteration, what are we doing? We are optimizing this M operator with respect to the best possible choice. And okay, we are not integrating over the discounted occupancy measure, but that's because we have all the power of like changing all the actions, so it doesn't matter, right? Like even if you integrate and you have no restrictions on the policies, then yeah, like every action you're gonna, so every state you're gonna choose the best action, right? Like that's the policy improvement step, the strong form. And so if we want to talk about intuition, I think it's quite intuitive, this form of the theorem, because it just tells us that, yeah, as expected, the gradient tells us to do something really similar to what policy iteration would be doing, right? So it's in a way connecting policy iteration and gradient ascent with this metric.
Well, the same thing happens in value iteration, right? So you have a Q function and you just take the action that maximizes the Q function, right? Like that is effectively the same thing. So instead of a gradient, it's like a maximization of the M parameter.
Sure. Sure. Okay.
But the point is that all of that look ahead is just being done with one step. I'm just taking the action that maximizes the Q function, and then I have to recompute a new Q function. I'm not taking the action that will result in sort of down the stream changes to the Q function at other states, right?
But maybe we shouldn't be surprised about that gradient ascent is a greedy procedure.
Yeah, we shouldn't be surprised. It's just sort of hidden in the normal form of the policy gradient theorem, whereas
Right.
somehow it seems more obvious that that's what is happening.
Oh yeah, yeah. Okay, yeah. So the normal form of the policy gradient theorem is really obscure, like this form here, compared to the previous one, right?
Right. Yeah.
Because now you're taking the derivative of log and like how did it happen? But this form in the middle, that's fine. That's just the same thing as what we had before.
Right.
Yeah. All right. Good. I think I'm running out of topics for planning, by the way. Are you excited of moving on?
What is the next thing?
I think batch RL. Well, we have two other topics, online RL and batch RL. I was thinking batch RL is shorter. Yeah.
I guess you talked about Polytech, and Polytech is a little bit of online RL. It doesn't really need a simulator.
Polytech doesn't help us that much in online RL. It's not. It's an unfinished project in online RL. We don't know how to add exploration and prove that we did the right thing.
By you mean you don't know how to add exploration? Do you mean you don't know how to add non-optimistic exploration?
We don't have a way of starting from Polytech, modify it in some simple way, and get some regret guarantees for some interesting case, like all Q functions lie close to the span of the features.
Okay. I mean, I guess the most similar thing would be the PCPG algorithm, but they do some funky stuff.
Oppo.
Wasn't Oppo more just LSVI with like a soft map?
No. Oppo is Polytech, but for the mixture MDP case, for that case, you can prove everything.
Oh, okay. Because I always thought of Oppo as our algorithm, but instead of the argmax, they took the softmax. So they do like a softmax step as opposed to.
Do they do VTR?
They do.
No. Oh yeah. I think that they had to modify everything. Yeah, like the original version was like, okay, you should stop
LSVI.
recording.
It was LSVI with.
You should stop recording.
Oh, okay.
By the way, cut this last